Rational and irrational numbers, 3.3 in our Pearson textbook. So the formulas for area and circumference of a circle involve pi, which is not a rational number because it cannot be written as a quotient of integers. A quotient meaning a fraction. We can't write a number x over y that equals pi, okay? What other numbers are not rational? So any number that cannot be written as a fraction is called irrational. And we'll get to that in a second. Basically, any number that has a non-repeating, never-ending decimal is what we're going to see an irrational number to be. These are rational numbers. And these are not rational numbers. So how are radicals that are rational numbers differ? How do they differ from radicals that are not rational numbers? So what we see is the square root of 100, the square root of 0.25, the cubed root of 8, 0.5 and 5 over 6, and 0.8 squared are not even radicals. 9 64ths square rooted, and the fifth root of negative 32. If you put all of these into your calculator, the radicals, you'll see that you get a real number. If you put these into your calculator and press enter, you're going to see that you get a non-repeating decimal. Okay, so a number that we couldn't write as a fraction is really what that comes down to. So what we see is that these ones are perfect squares, cubes, etc., whereas these are not. Which of these radicals are rational numbers and which are not? How do you know? If you put them into your calculator, you get nice numbers for these three, and you do not get very nice numbers for those. Okay, so which other radicals can be written as rational numbers? Basically anything that is a perfect root. So I had a few examples of rational numbers. The cubed root of 2.744 is, okay, because if I put it in my calculator, it equals 1.44. The square root of 169 over 144, because each of these are perfect squares, and any number written as a fraction will be rational. Others that are not rational would be the square root of 27.44. Okay, you get a random non-repeating answer. Square root of 2 doesn't work. The square root of 142 over 72, any number that's not a perfect square. So defining a few of these, a real number includes the entire number line. Okay, so a real number can be a whole number, it can be an integer, so negative, it can be positive, it can be rational, or irrational. So basically every number is a real number. A natural number is our positive numbers, so 1, 2, 3, etc. A whole number is all of our naturals plus 0, so 0, 1, 2, 3, onwards and upwards. An integer includes our positive and negative whole numbers and 0, so negative 2, negative 1, 0, positive 1, positive 2, and we can continue on in each direction here. A rational number is a number that can be written as a fraction. Some examples, again, could be just 5, the square root of 9, the cubed root of, 27 over 8, anything that comes out as a nice number. An irrational number is a number that cannot be written as a fraction. Our irrational numbers also have a non-repeating, never-ending decimal. So to represent these, I've just pulled an image off of the internet. Natural numbers are kind of the smallest subset. Remember, those were 1, 2, and 3. Whole numbers include natural numbers, but they also included 0. So whole numbers were 0, 1, 2, 3, etc. Integers include both our natural numbers and our whole numbers because 0, 1, 2, 3 is included but we also include all of the negative integers, okay? Rational numbers include all of these, all right? Rational numbers, again, were anything that can be written as a fraction, because we can write a whole number as a fraction. Remember, it's just that number over 1. Real numbers encompass all of our rational numbers, but they also encompass irrational numbers as well. Irrational numbers have no subsets like these guys did. Irrational numbers, the radical is the exact value. So I don't ever write a decimal if it's an irrational number. I'm going to leave it as the square root of 5 or the cubed root of 7. Okay. To determine the approximate value, we can use a calculator. So putting the square root of 5 into our calculator, we get 2.236, and it just goes on and on. The cubed root of negative 30 is negative 3.107, on and on and on. Okay, so another method without a calculator is to use what we know of our perfect power. So for example, if we have the square root of 5, the nearest perfect powers for the square root of 5 would be the square root of 4, okay, because the square root of 4 is equal to 2. And the next nearest would be the square root of 9. Okay, so the root 5 is trapped between those numbers. What we do is we draw a number line, and we're going to include our roots on there. So the square root of 4 and the square root of 9. And I know that the square root of 4 is 2 and the square root of 9 is 3. So I'm going to put all of that information on. And then what I'm going to do is I'm going to place our number on this number line. So the square root of 5 is pretty close to the square root of 4. In fact, if I divided the root 4 to root 9 into 5 sections, so the square root of 6, the square root of 7, the square root of 8, and then the square root of 9, I get 5 equal really nice sections. That means that each division would be 0.2 or 1/5 of this number line. So I can approximate that root 5 is approximately, so we use the wavy equal sign, 2.2. Okay, and we knew that from our calculator test earlier. We're going to do the same thing for the cubed root of negative 30. The closest perfect power would be the cubed root of negative 27 and the cubed root of 64, because the cube root of negative 27 is negative 3, and the cube root of, negative 64 is negative 4. So we put those on our number line here. Our number line is backwards, don't forget, because negative 3 comes before, negative 4. This is on its way to 0, and this gets larger and larger in the negative direction. So the cubed root of negative 64 and the cubed root of negative 27 I put on there as well. And this one doesn't divide really nicely. Between negative 64 and negative 27, there's way too many divisions. It's not as nice as our previous example here. So we're just going to approximate the best that we know how. So the cubed root of negative 30 is much closer to negative 27 than it is to negative 64. All right, so I would approximate that the cubed root of negative 30 is approximately, I don't know, like this would be negative 3.5. Let's say negative 3.1, for instance. All right, which we know is really close based on our actual calculated value. So if you are going to use a number line or approximate irrational numbers, approximate means don't use your calculator, and you need to show your work of creating these kinds of number lines using the closest perfect powers on either side of our irrational that we are looking at, or irrational number, sorry. So place the fourth root of 12 on a number line. Pause the video and give this one a shot. Remember, the fourth root means any number to the 4 would equal what's underneath here. All right, so I've gone ahead and identified my two closest perfect powers, the fourth root of 1 and the fourth root of 16, because 1 to the power of 4 is 1, 2 to the power of 4 is 16. Those are the closest two. Place these on my number line and put the fourth root of 12 pretty close to 16, the fourth root of 16. Therefore, it looks like I would say this is about 1.8 maybe. So the fourth root of 12 is approximately 1.8. I'm not using my calculator at all. Placing irrational numbers on the number line. Here I'm not asked to approximate, so I'm going to go ahead and calculate each of these in my calculator and just write them down so I have a good idea of where they should fall. All right, so we've gone ahead and just calculated these, and I see that the biggest number here is 3.14, or pi. And the smallest one is our negative 0.145, so the cubed root of negative 8 over 7. So my number line needs to extend from beyond negative 1 to beyond 3. So I'm going to go from 4 down to negative 2. It's not perfect, but that's fine. Placing our numbers on here, really close to negative 1 would be the cubed root of negative 8 over 7. At approximately 1 would be the square root of 4 over 5. About 1.5, I've got the fourth root of 5, and just beyond 3, I've got pi. Okay, so we're just putting them on a number line, and we're writing what was given in the question, not our approximate values from our calculator. Pause this video here and put these on a number line. All right, so I've put these into my calculator and gotten the approximate values. I can see very quickly that the cube root of 28 is not a rational number. It is irrational because it was never ending, not repeating. Because this is a real number, these ones are all rational. I should say not real numbers, but they were whole numbers, so or had a decimal that was repeating or ending. Putting these on the number line, everybody kind of works out there. It's a bit of a bigger number line, so I just went up by 2s. Yeah. For your exit task, plot each number from greatest to least and then identify the rational and irrational numbers. So exactly what we just did here. I'm going to pause, and you should too. Take a look at it and then double check your answer. I've put my numbers on my number line, and in doing so I used my calculator to approximate. I found that the first 3 are rational and the last one here is irrational. Go ahead and take a look at your demand line and do some practice. What you should be able to do is approximate without your calculator and put them on number lines.